Hello everybody, Namaskar. So in the previous lecture I have started the discussion on the ejector refrigeration cycle, so which is very attractive cycle or promising cycle for the renewable energy application. So in this lecture also I will continue the same thing, or we will discuss some other aspect of the ejector refrigeration cycle. Okay, so I will first discuss about the performance characteristics of the ejector refrigeration cycle. So how the performance parameter will vary with respect to the different operating parameters. Okay, so in this diagram we can see that how the COP and entrainment ratio mu that is varying with respect to the different temperature. So I will discuss how the different temperature, that means the three main temperature: evaporator temperature, condenser temperature and the generator temperature. So how the entrainment ratio, so this is the case 2, okay, where the entrainment ratio is not given but three temperatures are given. So how the entrainment ratio will vary with respect to these three temperature, or the other performance, how that will vary. Okay, so in this diagram you can see that for the defined refrigerant, okay, we can see the how the COP and entrainment ratio will vary with respect to the evaporator temperature for the different refrigerant. Okay. So three refrigerant has been considered. One is the R134A and second one is the R600A isobutane, and third one is the R717, which is the ammonia. So you can see that as the evaporator temperature will increase, then your entrainment ratio that will also increase. Okay, so the increase of the entrainment ratio, that will basically the increase in mass flow rate in the evaporator. So that is basically the more favorable conditions in terms of the performance of the system. Okay. So that means the higher entrainment ratio, that will give the higher value of COP of the system. Okay. So as the evaporator temperature will increase, then entrainment ratio will increase and the COP of the system that will be also increase. For some values of the nozzle efficiency 90%, mixing efficiency 100% and diffuser efficiency is 87% and pump efficiency 60%. So total cooling capacity is 3.5 kilowatt and the condenser temperature is 35 degrees centigrade and generator is 90 degrees centigrade. So for this case, this is the performance characteristics of the ejector refrigeration system with respect to the evaporator temperature. Okay, similarly in this diagram the condenser temperature is varying from 25 to 45 degrees centigrade. So how the entrainment ratio and the COP will vary with respect to with the increase of the condenser temperature. So as shown in figure, that the with respect to the condenser temperature, with the increase in condenser temperature, the entrainment ratio that is decreasing, so that the COP of the system of that is also decreasing. Okay, so as you know from the general description of the vapor compression cycle, also you have seen that if you increase the evaporator temperature or if you decrease the condenser temperature, then your COP of the system will increase. So same trend we can see for this case also. Okay, so and also as if you recall the equations which I have discussed in the previous lecture related to the COP, then you can see that the COP is directly proportional to the entrainment ratio of the system. Okay, so that's why if the COP will increase, then the entrainment ratio will be also increase, or if the entrainment ratio is increasing, then the COP will also increasing. Okay, so here we can see that with the respect to with the increase of condenser temperature, COP decreases and entrainment ratio is also decreases. Now if you compare with the different refrigerant, then you will see that in case of ammonia, COP value is always higher, that we have already discussed, that is compare the COP of the ammonia is comparatively higher as compared to the other refrigerant. So the same trend we can see here also. And if you compare the entrainment ratio, then also you will see that in case of ammonia, the entrainment ratio is higher as compared to the other refrigerant. Okay. Then the third variation that you can see with respect to the condenser temperature. So if the condenser temperature increases, then the COP and also the entrainment ratio both will increases. Okay, both will increases. So that means the higher generator temperature, that is favorable for the system in term of the COP. Okay, so COP will be higher for the higher generator temperature, and for that case also entrainment ratio will be also higher. So this is the same behavior we have seen for the vapor absorption cycle also. For the vapor absorption cycle also, if you increases the generator temperature, your performance COP that will increase. So the COP of the system, vapor absorption system, increases with the increase in the generator temperature, and same behavior you can see for this case. Okay. So and the entrainment ratio will be also increase. So the increase of entrainment ratio with the increase of generator temperature can be easily explained by this way, that if you increase the generator temperature, then the inlet thermal energy, okay, or the thermal energy or energy of the primary fluid, okay, that will increases. Okay, and higher thermal energy of the primary fluid has the higher capability to entrain the more secondary fluid in the ejector. Okay, so that's why with the increase in the generator temperature, the thermal energy of the primary fluid that increases. Okay, so due to the increase of thermal energy of the primary fluid, the entrained amount of the secondary fluid that also increases. Okay, so due to that your entrainment ratio of the system that increases. Okay, and again the increase of entrainment ratio that will also give the increase of COP. Okay, so that means for the higher generator temperature you will get the higher COP as well as the higher entrainment ratio. Okay, so in the previous 3 slides I have discussed the performance characteristics of the ejector refrigeration system with respect to the evaporator temperature, condenser temperature and generator temperature, and what I have discussed in the previous slides that can be summarized or concluded by this way. Okay, so the conclusion is that for the given condenser temperature and generator temperature, if the evaporator temperature increases, then the QC, which is the condenser heat transfer, that will decrease, and QG, this is the heat transfer in the generator, that will also decrease. Okay, and entrainment ratio that will increase. Okay, so the cooling capacity that will also increase. So the COP of the system that will also increase. Okay, so that means with the increase of evaporator temperature, the cooling capacity increases, entrainment ratio is increases, and COP increases. Okay, so now in the second case, if the condenser temperature increases, the QC, condenser heat rejection, that will increases, QG, the generator heat transfer, that will also increase, the intermittent ratio, that will decrease, then the cooling capacity will decrease, and COP will also decrease. Okay. Now, with the increase of generator temperature, for this case the condenser heat transfer, that will decrease, Qg, that will also decrease, so the cooling capacity, that will increase, intermittent ratio, that will increase, and COP will also increase. Okay. So, that means the higher generator temperature or higher evaporator temperature and lower condenser temperature, these are the favorable to get the higher performance of the ejector refrigeration system. Okay, so what I have already told, that the ejector refrigeration system has been attracted in the R&D community, okay, for the renewable energy application. So, we can use the solar energy to drive the ejector refrigeration system, and many product has been developed based on the ejector refrigeration system, which is driven by the solar energy. Okay. So, solar energy can be used as a heat source for the ejector refrigeration system. So, the lower part, that means the flow diagram for the black color, you can see that lower side. So, this is the ejector refrigeration system which I have discussed in the previous lecture. Okay, same. So, after the condenser at point 3, this is divided into two parts. One part is going to the evaporator through the expansion valve. So, that means 5, 6, and then that will be used as a secondary fluid. Okay, and another part that is going to the pump, and then that is going to the generator where that will absorb heat, and then that will be used as a primary fluid for the ejector. Then primary fluid and secondary fluid, that will mix, and the pressure will rise from the evaporator pressure to condenser pressure at point 2. Okay, then the 2 to 3, this is the heat rejection process in the condenser. So, this lower cycle I have already discussed in the previous lecture. So, now if you want to use the solar as a heat input for this system, so that means the in the generator the heat energy, that will be the driven by or gained by the solar energy. Okay, solar energy is the heat source for the heat energy which is given to the generator. So, that is why we need a solar collector which will absorb the heat from the solar energy, and that energy will be converted, that transferred to the generator through some heat transfer fluid in the solar collector. So, that fluid is basically the transfer heat from the solar collector to the generator. Okay, so that means that heat transfer fluid will take heat from the solar collector and the given heat to the generator. Okay, so the solar energy in the solar collector, solar energy is converted to thermal energy, and this thermal energy is carried by the heat transfer fluid from the solar collector to the generator. And in between that, on TEC, that is the thermal energy storage, that is used, because the solar energy is the intermittent energy. So, that's why to store the thermal energy or to get the continuous operation of the vapor compression system, we can use a thermal energy which will supply the constant heat to the generator, and also the heat supply to the generator when the solar radiation is not available. Okay, so the TS can be used to continuous supply of solar constant supply of heat energy to the generator. Okay, so and on heat pump, on pump is used for the continuous flow of this heat transfer fluid. So, for this heat transfer fluid in between the solar collector and generator, many heat transfer fluid can be there are many options of the heat transfer fluid which can be used for this case. So, that may be the water if the temperature is below 100 degrees centigrade, or maybe the some oils or some brines okay, which can be used as a heat transfer fluid in between the solar collector and the generator. Okay, so various type of solar collector can be used for the ejector evaporation system. So, but in case of ejector evaporation system, the temperature required in the generator, that is maybe approximately 100 degrees centigrade or 100 to 150 degrees centigrade. So, even below 100 up to 90 degrees centigrade also the system can operate. Okay, so maybe the 100 degree plus minus 10 degrees centigrade, that is some general temperature or above that temperature is required for this application. So that's why the temperature required for the generator is approximately more than 90 degrees centigrade. So that's why the flat plate collector for which outlet temperature is approximately 75 degrees centigrade or 80 degrees centigrade. So obviously that is below 90 degrees centigrade. So that's why the flat plate collector is generally not suitable for the ejector evaporation system. Okay, but we can use the evaporated tube collector or the parabolic tube collector for this application. So for the evaporated tube collector, the temperature range is approximately 100 or 80 to 150 degrees centigrade. Okay, so this temperature is most suitable for the ejector evaporation system. So the parabolic tube collector also the temperature we will get with the different wide range. Okay, maybe 100 to 300 degrees centigrade. So the parabolic tube collector also can be used to drive the ejector evaporation system. And for the thermal energy storage, three type of thermal energy storage are available and which can be used for the solar application for the ejector evaporation system. So on maybe the sensible energy. So in case of sensible energy storage, you can see that during the energy storage the temperature will increase, and if during the discharging temperature will decrease. So that means during the heat transfer the temperature will change in case of the sensible energy storage. Okay, so according to this diagram, first diagram or the bottom of this slide, first diagram, for this case you can easily see that from the energy storage to an energy release. So during the energy storage, the temperature the energy stored in the system, the temperature will be decreased, temperature will increase. Okay, so the temperature is directly proportional to the energy storage. That means if the energy is stored, temperature will increase, if the energy is released, temperature will decrease. Okay. And but for the second type of energy storage system or energy storage device, for that case latent heat of the melting or solidification, that is basically used for the energy storage. Okay. So for this case you can see that during this process, the energy storage process, your temperature will remain constant. Okay. So as the diagram you can see the second diagram. Okay, so in the second figure you can see that during the energy storage process the temperature will remain constant. So because we are using the latent heat, so latent heat of melting or condensation, that is basically used for the energy storage purpose. So that's why during that process the temperature will remain constant. So the energy storage process, the temperature will remain constant, and also for the energy release process, all temperature will remain constant. So this type of energy storage system can give the constant temperature outlet for the ejector evaporation system. And third part is the thermochemical energy storage. So for this case, during the energy storage process, the temperature will be changed. Okay, but for this case the amount of energy storage that is very high as compared to the sensible energy storage and latent heat energy storage. Okay, so all the energy storage has some individual advantages and disadvantages for the various applications. Although the thermochemical energy storage, which is the latest technology to store the thermal energy, So individual advantage disadvantage means for the sensible energy storage, this is very simple. For the construction we can use simply solid material, so the we can make that any type of size, any type of shape as per our component. So there is no chance of leakage, something or other mechanical problem for this case. Okay, so that's why that respect the sensible energy storage, that is very suitable for this type of if you see. And but if you see in term of the other aspect like the amount of energy storage, so that will be lowest, okay, minimum for the sensible energy storage. And if you compare the system in terms of the amount of energy storage, then you will see that the thermochemical energy storage, that will give the maximum energy stored per unit mass as compared to the latent heat and sensible energy storage. So the in terms of the energy storage capability or capacity, the thermochemical is the best, and then latent heat, and then sensible type heat storage. Or if you see the simplicity so the most simple sensible energy storage, then latent energy storage and chemical energy storage. Okay, and if you see the in term of the temperature control, then you will see that latent energy storage that has the temperature that can maintain the constant temperature during the heat transfer process or the energy storage process or release process. But in case of sensible storage and in case of the thermochemical storage, both cases the temperature will change. So the constant temperature cannot be maintained for these two cases. Okay, so if the constant temperature maintenance is the main criteria for the energy storage application, so obviously that in his storage is most preferable. And if you use that the storage capacity is the main criteria, so obviously the thermochemical energy storage is most preferable, like that. Okay, so at last the different advantages and disadvantages for the vapor compression refrigeration system that has been listed in this slide. So there are many advantages which are listed here. So the various heat source we can use for this case, because the heat that may be the solar energy, geothermal energy, and also the industrial waste heat. And variety of refrigerant can be also used in the cycle. Then no vibration and no noise, because here compressor is not used but the pump is using. So for the pump there may be some noise and vibration, but that is lowered as compared to the compressor in the vapor compression system. Okay, so running cost is very low and can be used in the remote area. Running cost is very low because for this case the pump is using, and the pump work that is very less as compared to the compressor work, because for the pump is used to handle the liquid, and liquid density is very high as compared to the vapor or gas, and compressor is for the vapor. So in case of vapor compression system, compressor is used. In case of ejector refrigeration system, pump is used, and pump work is very small as compared to the compressor work. That's why the pump electricity consumption is also very negligible as compared to the compressor in the vapor compression system. So that's why the running cost for the ejector refrigeration system is very low, and it can be used in the remote area also, because for this case for the running of pump, the electricity consumptions of the pump that is very small. So that means the pump can be a battery driven. Okay, so that's why we can use this system any remote area where electricity is not available, and solar energy can be used as a heat input to that system. But in case vapor compression system, we need a huge electricity, and the high system and the large capacity system cannot be run without the electricity in case of vapor compression system. So that's why that system cannot be used in the remote area. The electricity must be required for the vapor compression system. So in that respect, this is the disadvantage of the ejector application system, that this can be used in the remote area also. And construction of this system is slightly simple, and this can be easily combined with the other system for the multi-generation operation. Okay, and some of the disadvantages that are the low COP and the narrow operating range. So in the previous lectures also I have discussed that the COP for all the heat driven system, that COP is very less as compared to the COP of the vapor compression system. Okay, and narrow operating temperature range. So for the ejector application system, for the off design operation or performance of the ejector application system, that is very bad. Okay, so that means if you change any pressure and any temperature and pressure at any side, higher and lower, and after some time you will see that this system cannot be that system will not operate. Okay, so that the operational range for the system, that is very less in case of vapor compression cycle. Okay, so that means for the certain operating range and certain operation or certain application, you have to design the different type of ejector application system, or the another option is that we have to make some flexible ejector where the operating condition can be easily changed, or the ejector can operate with the operating condition. So for that case, actually the nozzle area and the primary nozzle area, secondary nozzle area, and nozzle throat area, nozzle dimension, all are very important. Okay, so that's why we have to, if we made some nozzle or the ejector where the defined dimension can be changed with respect to the operating condition. So if you if you have a design flexibility for the ejector, then the system can be operate some wide range of application. Otherwise, there is the negative point of the ejector application system is that for the certain operating range you have to use the certain ejector application system to get the operation properly. Okay, so there are many advantages, so industrial advantages, and where we can use the renewable energy, or we can use the other waste heat from the industries to drive the ejector application system. Okay, so and for any remote area of the cooling, we can easily use the renewable energy to drive the ejector application system. Thank you.